functions in different ways. And first point, in general way of discussion related to function, and in second point, mathematical way of discussion related to function, and in third point we counted the number of functions, whereas in fourth point here the notations related to the function. Among those notations, again the first one is the definition of the function in set builder form. Okay, see, if a function f is a function from a to b, if f is a function from a to b, then we usually notate like this: f is from a to b, okay, such that f is from a to b such that f contains the ordered pairs x comma y, and those x comma y are in such a way that for every x belongs to a, for every x in a, there is y in b. Okay, and for every, you just look there, the word for every, okay, and there is, right, there is unique y. Actually you need to write here unique y. Okay, mathematically for every you can use the symbol for all. Okay, again this is equals to f is contains the ordered pairs x comma y such that for every, in the sense for all x belongs to a, there is, in the sense there exists. See, this symbol is used for there exist, and this symbol is used for all. For all x belongs to a, there exists unique y belongs to b, and this function f is always a subset of a cross b, and that's why we call it as a relation. So basically this is one way of notating a function, the definition of the function in complete mathematical way. Okay, just have a look. F is a function from a to b, and that f contains the ordered pairs x comma y such that for every x belongs to a, there exists unique y in b, and that f is again a subset of a cross b. Okay, and for suppose the next point related to this, b. If we have an ordered pair, f contains the ordered pairs of the format xy. If xy is an ordered pair of the function, okay, right, if fxy, if xy is an ordered pair of the function, then we will write that f of x is equals to y, or f is mapping, is connecting x to y, or we usually say that x f y, all are same. These are the different notations. Okay, if we have an ordered pair x comma y in the function, then we say that f of x is equals to y, or f is mapping x to y, or x f y. All these are same. Okay, xy belongs to f, f of xy is equals to y, f maps of x to y, x f y. All these four are equivalent statements. All this represents just one idea, and that means x comma y is an ordered pair of the function. Okay, and one more thing, yeah, these functions are also known as mappings. Sometimes we use the word. Okay, I will give you here. Next one, C. Functions are also known as mappings. Functions is equals to mappings. Right. Related to the notation, another point which is D. If f is connecting x to y, what I am saying, if f is connecting x to y, then this x is called, or this y is called, there are different names for this x and f. Okay, if f is connecting x to y, this y is called image of x, image of x with respect to, image of x with respect to the function f, and whereas this x is called pre-image of y. Okay, this is called what? Pre-image of y with respect to f. So all these are different notations related to the function. Okay, at a time just have a look. Once again I repeat for you. The first one is notation A, which represents the definition of the function. So different notations just we are discussing. Okay, so this is a definition of the function in mathematical way, and if an ordered pair is there in the function, then we say f of x is equals to y, or f is mapping x to y, or we just take x f y. And in the same way, functions are also known as mappings. That's another point. And one more idea is, if f is a function from x to y, this y is mentioned as image of x with respect to f, with respect to the function, and this x is called pre-image of that y with respect to the function. Once again I am repeating, y is the image of x and this x is the pre-image of y. Okay, just have a look. If f is a function from the first set having elements 1, 2, 3, 4 and second set is having the elements 1, 2, 3, 4, such that f is defined as a set containing the ordered pairs x comma y such that y is equals to x square. So first set 1, 2, 3, 4. Second set 1, 2, 3, 4. See, if we observe, there exist many relations. Okay, how many relations? These are 4, 2 power 4 into 4, 2 power 16 relations. Among those, some are functions and the number of functions are again 4 power 4 actually, because the number of elements are same. And among those number of functions, the rule of the function here in particular is y is equals to x square. So 1, we need to map, we need to connect this 1 to its square. So we know the square of 1 is 1 itself. And whereas 2, we need to connect it to 4. Okay, right. For 3 and 4, are there any elements for this? Right. There are no elements to connect that 3 and 4 actually. So it won't become a function. Since there are no elements to connect 3 and 4, okay, with this particular rule, we don't have a function here. Okay, right. Or otherwise I will give you another definition. Yeah, if f is equals to x comma y such that y is equals to x plus 1, and I will take another element 5 also in the second set. So now I have a function from the first set having the elements 1, 2, 3, 4 and the second set having the elements 1, 2, 3, 4, 5 with the relation that f ordered pair x comma y such that y is equals to x plus 1. So first set 1, 2, 3, 4. Second set 1, 2, 3, 4, 5. So as per this rule, 1 I need to connect for 2, 1 plus 1. 2 we need to connect for 3, 2 plus 1. We need to connect 3 for 4, 3 plus 1 and connect 4 to 5. So this is the function. And among those, if you concentrate on any one connection, one correspondence, okay, for suppose if you take this correspondence which is corresponding 2 to 3 with respect to this f. Since 2 is connected to 3 with respect to f, here we will write that 2 comma 3 is an ordered pair of the function, or f of 2 is equals to 3 we will say, or sometimes we will say that 2f3, okay, or sometimes we just represent it like f is mapping element 2 to 3, and in this case this 3 is called what? Image of 2, whereas this 2 is called what? Pre-image of 3 with respect to the function. Okay, just by observing the ordered pair 2, 3, we have all these notations and the terminology image and the pre-image. Related to every ordered pair, we have all these notations and the terminology. Okay, you just have a look related to this. A small example to explain about the notations of the function. Okay, once again, functional value is simply, for a function y is equals to f of x, functional value of f of x is f of a at x is equals to a. That in the sense functional value is different for different values of x. At x is equals to a, the functional value is f of a. At x is equals to b, if you take, the functional value is f of b. Okay, and for example here I have a function which is defined from integers to integers such that f of x is equals to x square, and for this particular function the functional value is 2 square at x is equals to 2. At x is equals to 2, the functional value is 2 square, which is 4. At x is equals to 3, the functional value is 3 square. We need to replace x with 3. Okay, at x is equals to, you may say something like sin x, at x is equals to sin alpha are you taking? At x is equals to sin alpha, the functional value is sin square alpha. So the functional value is different for different values of x. It depends on the values of x. So if this is x is equals to 2, the functional value is 4. If x is equals to 3, the functional value is 9. If x is equals to sin alpha, the functional value is sin square alpha. Okay. We have different types of functions as per the rule, and automatically we will have different functional values at different values of x. For suppose, I will give you another function. Yeah. I have a real function that in the sense, just have a look. A function g is from real numbers to real numbers, okay, such that g of x is equals to 2020 for all x. Just have a look. I have a function real numbers to real numbers such that the g of x is equals to 2020 for all x. Since it is 2020 for all x, what to say about it? Yeah. What is the functional value? What we are saying? We are finding functional value of the function g, functional value of g at x is equals to 7. Functional value of g at x is equals to 7 is simply nothing but g of 7, and the g of 7 again equals to which value? Which is 2020. Because g of x is equals to 2020 for all x, you just take any x, but that x is just related to 2020 only. Since we define that g of x is equals to 2020, as per this rule, g is a relation or a function which contains the ordered pairs x comma 2020 for all x belongs to the real numbers. You just take any number in the place of x, it just connects to 2020 only. So the functional value of g here it is what? 2020. Or you may say another functional value. What is the functional value at a 1 by minus 2019? Again the value is 2020 itself. Take any value, but it corresponds to 2020 only. The functional value of this g function at the point e power root of sin alpha. I am taking some value. No problem. E power root of sin alpha. It's a real value. For every real value, it just connects to 2020 only. So its functional value is 2020. So depending on the function, we will calculate the functional value. And the functional value of f of x is denoted by f of a, and its value is calculated by replacing x with a in the given function, just like this. Okay, just have a look. I will give you one more example. Right. So for suppose if h is a function with a definition 1 by x, then h of 2 is simply replacing x with 2, and that will become 1 by 2. H of t is simply 1 by t, and h of 1 by y. So we need to replace x with 1 by y, 1 by y, and on simplification this is equals to y. And then h of root z, replace x with root z, you get it as 1 by root z. And then h of 0. H of 0 means actually that is 1 by 0, and that 1 by 0 is not exist in the real values. So h of 0 is not a defined one. H of 0 is undefined actually. See, since h of 0 is undefined, then if 0 is there in the first set of this h, we don't call it as a function, because there is no corresponding element for 0 with respect to this function. Okay, if you say it as function, for sure 0 we have to exclude this 0 from the first set, or otherwise you just call it as a relation. Okay, but just these are the functional values related to that particular function. Okay, and I have another one. P of x is a function. Okay, for some time you just leave about the first set and the second set. Okay, P of x is a function from a set A to set B, and the rule of the function is this: x plus 1 by x minus 1. Here our task is to find P of 3 power 2020 plus P of 3 power minus 2020. See, this is one functional value and that is another functional value. We need to add the sum. Okay, that in the sense replacing x with 3 power 2020. Okay, and to calculate this one, we need to replace x with 3 power minus 2020. Okay, and for this problem, direct replacement of that number 3 power 2020 in the place of x will give you somewhat bit calculation. So to avoid this, first of all, yeah, I am erasing this. First of all, I will try to find some some constant p of k plus p of k power minus 1. Why? Because if this is some k, this value is the same constant to the power minus 1. So you just try to calculate that p of k plus p of k power minus 1. So this is equals to p of k plus p of k power minus 1 is simply what? P of 1 by k. Okay. And what to say about this p of k? This p of k is simply nothing but k plus 1 divided by k minus 1. Because p of x is that x plus 1 by x minus 1. So for p of k, replace x with k. So k plus 1 by k minus 1. Plus what to say about p of 1 by k? So we need to replace x with 1 by k. So 1 by k plus 1 divided by 1 by k minus 1. We need to simplify this. So as a part of simplification, if you go, the first term is as it is, which is x plus 1 k plus 1 divided by k minus 1. And the second term, you just took LCM, it becomes like 1 plus k by k, and here it becomes like 1 minus k by k. So plus 1 plus k divided by 1 minus k. Is it clear? Just have a look. The first one is k plus 1 by k minus 1. And the second one is 1 plus k by 1 minus k. See, this is k minus 1 and that is 1 minus k. This is k plus 1 and that is 1 plus k. 1 plus k and k plus 1 both are same. But this k minus 1 and 1 minus k are differ by a minus sign. So I have a chance to rewrite it like this. K plus 1 divided by k minus 1 minus k plus 1 divided by k minus 1. So this minus for this k minus 1 become 1 minus k only, and that difference is 0, right? So for this function p of x is equals to x plus 1 by x minus 1. Take any constant k, that p of k plus p of k power minus 1 gives you 0. So with this idea, directly we will say that the sum of these two functional values is 0. No need to do further. So this is a somewhat a special function, okay, special rule. Usually it gives you these type of simple problems, okay, where you will calculate that p of k and p of 1 by k. If you add, the result is 0. Just have a look. So for suppose in 6th point we are going to discuss about domain, codomain and range as we discussed in relations. F is a function from the set containing 1 to 3 to another set containing a, b, c, d. Okay, and the function contains the ordered pairs 1a, 2c, 3c. So the arrow diagrammatic representation for this function is 1 maps to a, 2 to c and 3 to c. Right. Now what is the domain of f? As we discussed in relations, here again the domain of f is simply nothing but the first set. Okay. See, you just look there. The domain of a relation is the first elements of the relation, the first elements of the ordered pairs of the relation. Here, for a function, every element of the first set must have a unique correspondence. Since every element of the first set has a unique correspondence, in the case of functions, for sure, the domain of f will become the first set. Once again, I am repeating you. If f is a function, for sure the domain of f is directly equals to the first set. Whereas if f is just a relation, okay, domain of a relation is just subset of the first set. Why? Because there are some chances where some elements of the first set are not corresponded, not related, okay, and that's why in the case of relations the domain is subset of the first set. Whereas in the case of function, the domain is always equals to the first set. The definition is same as we discussed in the relations. The definition is simply the first elements of the ordered pairs of the function. Okay, 1, 2, 3 here, and that is A. Whereas coming to the codomain of f, codomain of f is again directly equals to B. Okay, domain of f is the first set of the function, codomain of f is the second set of the function. Whereas coming to the range of f, okay, range of f is simply the second elements of the ordered pairs. Okay, see here, if you look, 1 is related to A, 2 is related to C, 3 is related to C. So among these 4 elements of the second set, only A and C have a relation, have a connection with the elements of first set. This B and D don't have, and that's why the range of f here itself just contains A comma C. When you observe the ordered pairs, the second elements of the ordered pairs, if you observe, A and C itself. So range of f is set containing AC, and this range of f set containing AC are also denoted like A is simply f of 1. Is it right? As per the notation, since 1 is connected to A, we say that f of 1 is equals to A. Whereas coming to C, f of 2 is C, f of 3 is also C. So I may write f of 1 comma f of 2 comma f of 3. Range of f is a set containing the second elements of the ordered pairs, and this is in another way denoted like this: f of 1, f of 2, f of 3. And see, f of the elements of the first set, and that's why totally range of f is denoted by f of A. Once again, domain of f is simply nothing but the first set. Codomain of f is nothing but second set directly. Whereas the range of f is nothing but range of f is the second elements of the ordered pairs, and if you indicate them, you have a chance to rewrite like this: f of 1, f of 2 and f of 3, and that's why there is a chance to represent it like f of A. At the end, you need to memorize always domain of f is the first set A, codomain of f is B, and range of f is simply f of A. So f of the elements of the first set, and that f of A, if you observe, always is a subset of the codomain. Is it right? Because range of f here contains only AC, but second set is total ABCD. So always range of f contains few elements of the second set, and that's why we say that always range is a subset of codomain. Okay, so this example just gives you some idea related to the domain, codomain and range. Domain, for the case of functions, domain is directly the first set, codomain is the second set, range is the second elements of the ordered pairs, and you just denote that range of f by f of A. Okay, just have a look. This is something about the domain, codomain and range. Okay, so depending on the first set and second set, domain and codomain of f, there are different specific names for the functions. If f is a function from set A to the real numbers, then we call it as real valued function. If codomain is the real numbers, we call it as real values. If domain is the real numbers, we call it as real variable function. Okay, if x values are real, then we call it as real variable. If the results are real, we call it as real value. If both first set and second set are real numbers, we call it as real function. In most of the case, we will use the word real function, and all mathematical functions which we use are real functions itself, because they are from the real numbers to real numbers. Okay, and whereas in this case, if the first set and second set are integers, we call it as an integral function, and if first set and second set are rational numbers, then we call it as a rational function. Okay, so f is an integral function that in turn represents that domain is set of integers, codomain is set of integers. F is a real function that represents that domain is set of real numbers, codomain is also set of real numbers. If f is a rational function, then in that case domain and codomain are rational numbers. Okay, just have a look. This is something about the first set, second set. That means domain, codomain and range. Okay, in the next class we are going to discuss the way of finding range and the way of finding domain for different types of functions. Okay, initially we will start with the standard functions, and then we can extend it for other functions also. Finding domain and range in the next point, in the next class. Okay, just have a look.